to chapter 3. Where we'll define Lebesgue measurable functions versus measurable sets. And what we're trying to do is really mimic what Riemann does in setting up Riemann integration as we establish Lebesgue integration. So we'll define in this chapter measurable function, and it's measurable functions that we'll integrate. So following that shady experience near the end of chapter 2 with non-measurable sets, we're trying to avoid non-measurable sets. So all of the following is motivated by those non-measurable sets. We want to follow Riemann's ideas of Riemann sums and little rectangles and limits. So what we'll do is, this won't be the verbiage exactly that we use, but we'll introduce an idea of sort of a Lebesgue sum of quote unquote rectangles. The heights will be determined by function values, and the bases will be determined by the measure of the set. So when we go looking for the bases of these rectangles, we better make sure the bases are measurable sets. So in defining Lebesgue integrals, we can only consider functions which will give rectangles with measurable bases. So that's the point of the following definition. Not quite clear how it fits in exactly, but there should be some motivation, thinking in terms of base times height rectangles, base being sets this time. In the Riemann setting, you partition up the x-axis and you determine heights using x values from subintervals. We're going to do a little bit different in here, effectively partition up the y-axis. And what we'll do is we'll try to capture sets on which the function takes on certain values. So the height will come first, and then we'll project back and look for bases. That's pretty oversimplified. Proposition 3.1 gives 4 properties, each equivalent to the other. Let the function f have a measurable domain E. The following are equivalent. The set of x values for which f of x is greater than c is measurable for all c a real number, is equivalent to the set of x values such that f of x is greater than or equal to c is measurable for all c a real number, is equivalent to the set of x values for which f of x is less than c is measurable, or the set of x values such that f of x is less than or equal to c is measurable for all c a real number. So we're not exactly projecting back single function values, but we'll ultimately use function values in these ideas to find the bases of those Lebesgue rectangles. And because we will only consider a function that satisfies these properties, we'll be getting measurable bases out. Little final comment, each of these properties implies that for each extended real number or the infinity symbol, that the x values such that f of x equals c is measurable. It's not so much f of x equals c, we'll have a little wiggle room, and we'll partition up the y-axis and look for function values in a little strip, a little range. And that little range will project back as an intersection of a couple of these kinds of things. And from there, we'll find bases. So crudely put, that's the plan. Let's go through and establish that these 4 things are equivalent to each other. Okay, so let's show equality of the first 4 things. We're alleging sets are measurable, and the measurable sets form a sigma algebra closed under complements, and I see some complement relationships here between some of these. The sets 1 and 4 are complements of each other. Either f of x is greater than c or f of x is less than or equal to c, provided f of x is defined, which it is for all x and e. E's the domain of the function. So the set in part 1 and the set in part 4 complements each other. If one is measurable, then the other one is measurable. If one is not measurable, then the other one's not measurable for a given C value. Similarly, 2 and 3, these involve complementary sets as well. F of x greater than or equal to C versus F of x strictly less than C. Since these involve sets which are pairwise complements of each other, then we've got 1 and 4 are equivalent statements and 2 and 3 are equivalent statements. So we've paired them off. If we can just show equivalence between one of those and one of the other ones, then we can tie off the equivalence claim. Let's consider all x in E such that f of x is greater than or equal to C. So looking at part 2, that's a set we would have from part 2. That can be written as an intersection from k equals 1 to infinity of x in E such that f of x is greater than C minus 1 over k. Intersect those up, f of x greater than C minus 1 over k. K approaches infinity, and that'll yield all x values for which f of x is greater than or equal to C. Whoops. And that's the claim. So we do get equality in those two sets, just a set argument. So if we have measurability of these sets, that is if part 1 holds, we're in a sigma algebra, then the intersection, countable intersection of those sets will be measurable, and this will hold. That is, part 2 will hold. So if part 1 holds, then part 2 holds. 1 implies 2. Let's reverse that implication. We can take the set of x values such that f of x is strictly greater than C. I'm looking at part 1 type sets now. And we can write that as a union of x values such that f of x is greater than or equal to C plus 1 over k. It's an f of x greater than or equal to, that's a part 2 type thing. So if part 2 holds, all of these sets are measurable. We're in a sigma algebra. Their countable union is measurable. The equality of the sets is quite similar to what we had here, except involving unions instead of intersections, and the inequalities aren't strict in the same places they were in the previous argument, but those sets are equal. If 2 holds, everything here is measurable. The right-hand side is measurable, and so the left-hand side is measurable, and part 1 holds. So 2 implies 1. So we've got equivalence between 1 and 2, and by transitivity of equivalence with the implications, all these things are equivalent to each other. So actually a fairly brief argument to establish that those 4 things are equivalent. We're still left with a little loose end about equality. For all real numbers, all extended real numbers C, the set of x values for which f of x equals C is a measurable set. We are allowing the functions to take on infinity as a value, which is a little weird, but we're dealing with extended real numbers here. Okay, so if any one of 1 through 4 hold, then all of them hold because we've shown they're equivalent. So we can use all of them. If we take 2 and 4 for a given real number C and intersect those two, the x values such that f of x equals C is the x values for which f of x is greater than or equal to C, intersect the x values for which f of x is less than or equal to C. And both of those sets on the right-hand side are measurable if we assume the conditions above. So their intersection is measurable. And so this set concerning the equality of the function with C is a measurable set. To deal with the extended real number C, these do not deal with real numbers. I'm sorry, do not deal with the infinity. They deal only with real numbers. So we need to deal with the C equals infinity case separately. The x values for which f of x equals infinity, we can get to that set of x values by intersecting all sets of x values for which f of x is greater than k. K equals 1 to infinity. The intersection of all those removes all finite values of a function, all x values that produce finite values, leaving us only with the extended real number stuff, the infinity. Each of these is measurable by, it's a greater than, part one. Each of these is measurable, so their countable intersection is measurable. We're in a sigma algebra. And so that final conclusion holds. All right, we're quite interested in functions that satisfy these for the reasons explained. These set of x values, kind of projecting back in some sense, we'll talk about inverse images here shortly. These relate to bases of rectangles. Well, they involve x values, so there's that, and they'll involve intersections of these. So we will get bases of rectangles which will be measurable. When we consider such functions satisfying that condition, it's so important. That's what a measurable function is. An extended real-valued function defined on a measurable set is a measurable function or Lebesgue measurable function if it satisfies any one of 1 through 4 in that previous proposition. If it satisfies one of them, it satisfies the other 3 as we just showed. So that's what we mean when we say measurable function. Probably played up the word Lebesgue when we were doing Lebesgue measure. With the functions, I'll probably just refer to measurable functions. And we often just refer to measurable sets and didn't insist on them being called Lebesgue measurable. But measurable functions are the kinds of functions that we will Lebesgue integrate. I might emphasize Lebesgue integral a bit because we've got, in the back of our minds, all that Riemann integration stuff, and we're outgrowing that. Second proposition says, let f be defined on a measurable set, then f is measurable if and only if for each open set O, the inverse image of O, f inverse of O, is measurable. Okay, proof of this is based really on the fact that you know what an open set looks like. An open set is a countable disjoint union of open intervals. What we're doing here is, at least in the first and the third, in this definition of measurable function, we're taking inverse images of open intervals. These x values are the inverse image of output values greater than c. This is the inverse image under function f of the interval c to infinity. This is the inverse image of the interval negative infinity to c, wherever the function is less than c. These are inverse images of closed unbounded intervals, by the way. But the proof is based on the fact that we know what open sets look like. All right. Let's see, if and only if result. First, if the inverse image under F of every open set is measurable, then, well, like we were saying, C to infinity, why, that's an open set, so its inverse image is measurable. The inverse image of C to infinity under function F, inverse image, I'm not talking anything to do with inverse functions, these are inverse images, though the notation's the same as inverse function. I don't know anything about one-to-oneness, so we're talking inverse images in this. The inverse image of C to infinity would be the f of x values that lie in the interval C to infinity, be all x values such that f of x is greater than C. So this set is exactly an inverse image of an open interval. If this set is measurable, then by theorem 3.1, part 1, a function that satisfies any of those 4 parts is a measurable function. Really, it's a definition. But this function then satisfies part 1, and so is a measurable function. So if inverse images of open sets are measurable, then the function is measurable. Now we need, so that part was easy. Now we need to reverse it and say, suppose f is measurable, let O be an open set. We want to show the inverse image of O is measurable in the second part. Well, you like intervals, don't you? I know what open intervals look like. I like open intervals. I know open sets are made out of open intervals. And there's been a lot of talk about open intervals here in this definition of measurable functions. So let's take set O. It is a countable disjoint union of open intervals. And the disjointness doesn't particularly concern us, but you know open sets are countable disjoint unions of open intervals. I'm going to deal with this in terms of bounded intervals. Any unbounded interval can be written as a countable union of bounded open intervals. Any unbounded open interval can be written as a countable union of bounded open intervals. So I need the word open somewhere in here. So in the classification of open sets, we didn't have the word bounded, but without loss of generality, we can drop the disjoint and insert a bounded. This is the argument. Any unbounded open interval can be written as a countable union, drop disjoint, countable union of open intervals. I think that's pretty clear. So we can take set O and write it as a union of bounded open intervals. Not necessarily disjointly though. Okay. Then say those open intervals, those bounded open intervals, the I sub k's, have endpoints A sub k and B sub k. We can write those as capital B sub k intersect capital A sub k, where capital B sub k is the unbounded open interval from -infinity to b, and A sub k is the unbounded open interval A sub k to infinity. You intersect these two under the condition that A sub k is greater than B sub k, and you get that little interval there. Why drag these into the conversation? Oh, because of the definition of measurable function. I know what inverse images of those things look like. So if we can take set O and write it in terms of these things, and we know that these things behave well, their inverse images are measurable, we'll conclude that O has an inverse image which is measurable. Since f is a measurable function, the inverse image of B sub k, this thing, and A sub k, this thing, both of those are measurable sets. That's the definition of measurable, proposition 3.1, parts 1 and 3. Okay, well, we can write O in terms of these A sub k's and B sub k's with some unions and some intersections, countable unions and countable intersections, countable unions and, well, countable intersections ultimately as well, but that's sigma algebra stuff, so we're good. O, we've written as a union from k equals 1 to infinity of the I sub k's, and the I sub k's individually we've written as B sub k intersect A sub k. We've got an inverse image of a union of these intersections. Inverse image of a union is a union of the inverse images, properties of functions and inverses. The inverse of an inverse image of an intersection is the intersection of the inverse images. So we've ultimately got the inverse image of O written as a countable union of intersections of measurable sets. We commented on the last slide that F inverse of B sub k and F inverse of A sub k are both measurable. So we've written the inverse image of O as a countable union, countable intersections of measurable sets. So it's measurable. That is, F inverse of O is measurable using the sigma algebra properties that we have of measurable sets. And so F inverse of O is measurable, and that was the converse, the other claim we were trying to show. Okay. Given this behavior of measurable functions as they treat open sets in terms of inverse images, the next result is a real piece of cake. So proposition 3.2 makes the proof of the next claim. The next claim is real valued function that's continuous on its measurable domain is measurable. So continuous functions are measurable functions, to oversimplify a tiny bit. Awesome. I know how continuous functions treat open sets as well in terms of inverse images. So that's what will make proposition 3.3 work. Continuous functions are measurable. Now, the plan here ultimately is to show that Lebesgue integration is a generalization of Riemann integration. You know continuous functions are Riemann integrable. We're about to show that Continuous functions are also measurable, and it's the measurable functions that we're going to integrate. We will define the Lebesgue integral of all measurable functions. Details to follow, great number of details to follow. We won't be able to deal with a function that yields an infinity minus infinity thing. Infinity minus infinity, and I'm talking about integrals, and integrals will be, crudely put, their limits. Just like for Riemann, there's some kind of limiting values. Well, limits can be infinity, and when we're dealing with functions that can be both positive and negative, I gotta get a problem potentially like this. That can't be resolved. But barring that little concern there, we will define the Lebesgue integral for all measurable functions, which don't deal with some sort of meaninglessness. So we want to show Riemann integration implies Lebesgue integration, integrability. So continuous functions is a good place to start. You know continuous functions are Riemann integrable. Yeah, they're Lebesgue integrable as well. It'll take us a while to get there, but we'll establish that. And not only that, but Riemann and Lebesgue agree on the value of the integral. When a function is Riemann integrable, Riemann and Lebesgue will agree on the value of the integral as well. And we've classified functions which are Riemann integrable. Bounded functions on closed and bounded intervals are Riemann integrable if and only if the set of discontinuities has measure 0. So Lebesgue will be able to deal with those functions as well, and will give the same value that Riemann gives. So what lies in our short-term future is some discussion of measurable functions, and what lies in our long-term real analysis 1 future is Lebesgue integration. So we're getting the setting in chapter 3 for Lebesgue integration, and we'll do the integration itself in the next chapter. All right, real valued function that is continuous on its measurable domain is a measurable function. All right. If a function is continuous, for all open O, the inverse image of O is open relative to the domain of F, a property of continuous functions in a topological setting. It's pretty much the definition of continuous. But you'd do this in senior level analysis. You'd show inverse images of open sets are open. There's a link to some notes from senior level analysis that establish that. So if we take open set O, we know F inverse of O is E, the domain of the function, because I didn't explicitly say, but the domain of the function intersects some open set U, let's call it. So the inverse image of O is an intersection of measurable sets. Saying F is a measurable function, saying F is a continuous function gives us this kind of behavior where E is the domain. Measurable domain, there we go. And we've got hypotheses that E is measurable, given right here. So E is measurable, U is open, so it's measurable. So the intersection is measurable. That is, F inverse of O for an arbitrary open set O is a measurable set. F inverse of O is measurable. We just saw if F inverse of O is measurable for any open set O, then the function must be measurable. So the previous proposition we did shows that F is a measurable function as claimed. Continuous functions are measurable. Arguably, this is really a corollary to what we just showed because it's fairly easy given the previous result. Let's make a mention of monotone functions. Excuse me, the book does. It saves the proof as an exercise. But recall that a monotone function can have, defined on an interval, can have at most countably many discontinuities. There's a link to some senior level analysis notes that contain that. This is useful in the proof of the following. The proof of the following is one of the exercises, problem 3.24. says a monotone function that's defined on an interval is measurable. And I know something about the discontinuities. I know there's at least countably many of them. Actually, I know what kind of discontinuities there are as well. They're jump discontinuities. So left is a homework exercise, but this property of discontinuities of monotone functions you'll find useful in the proof of that. Proposition 3.5 says, let f be an extended real valued function defined on set E. If f is measurable on E and f equals g almost everywhere, then g is measurable on E. So functions that are equal almost everywhere, if one is measurable, then the other is measurable. Remember, almost everywhere means the functions in this setting, it would mean the functions differ on a set of measure 0. And we're going to be, from a perspective of Lebesgue integration, very disinterested in sets of measure 0. They're not going to affect the values of Lebesgue integrals. Secondly, for D, a subset of E, which is measurable, f is measurable on E if and only if f restricted to this subset of its domain is measurable and f restricted to the complement of that set D with respect to the domain is also measurable. If f restricted to D is measurable and f restricted to E set minus D is measurable. If and only if. Let's prove that. Okay, first, measurable function f equal to g almost everywhere. Suppose f is measurable on E. Saying a function is measurable on a set comes with the implication that that set itself is measurable. Let's define set A to be where the functions differ. The x values in the domain of f where f and g are different. Well, f and g are equal almost everywhere, so the set of x values where they differ must have measure 0, or if you like, outer measure 0. Now we're going to take the set of x values such that g of x is greater than c and write it as the x values in A where g of x is greater than c. All right, so this is where g of x is greater than c, but g of x and f of x are different. That's what set A was all about. So what's f of x doing here? I don't know. Could be, it's different from g, so I don't know. It could be greater than c also. It could be less than c. I don't know what f is doing. Remember, this is a small set, though. This is a subset of a set of measure 0. Let's union that with the x values in E such that f of x is greater than c. So this includes all of the places where f of x is greater than c. What's g of x doing there? Well, the same thing f is, except on those points in set A where f and g are different. So let's remove those. Let's intersect this with E set minus A. So this keeps the x values where f of x is greater than c, and f and g are the same. So when f of x is greater than c and f and g are the same, g of x is greater than c. So we got two kind of places where g is greater than c, where it agrees with f and f is greater than c, and where it disagrees with f and g is greater than c. So the x values for which g is greater than c can be broken into these two pieces. Well, there's 3 pieces involved, and each of those constituent pieces is measurable, and that's how we'll draw the conclusion of measurability here. This could be done for any real number c. The set identity holds. The measure of set A is 0. This is a subset of set A, so this set is measure 0 as well, outer measure 0 if you like, and outer measure 0 sets are measurable. So I threw monotonicity somewhere in there, I think. But this is a measurable set. It's an outer measure 0 set. How about this set? Forget the intersection, just the stuff in the set brackets there. That's measurable because function f is measurable. That's the definition of measurable. Proposition 3.1 was at the first part. but these kinds of sets were measurable when dealing with measurable functions. It was a definition of measurable. How about E set minus A? Well, A is measurable because it's got outer measure 0. E is measurable because we're dealing with a function f measurable on set E. E is measurable. So E set minus A is also measurable because we're in a sigma algebra. E set minus A is E intersect A complement. If you want to get down to the intersections, the unions, and the complements, very hands-on, but if we've got a sigma algebra, or just an algebra, we've got closure under set minuses, relative complements. So each of these three constituent sets is measurable. We've got some unions and some intersections. So the set which they equal, x values for g of x is greater than c, that's a measurable set. We could do this for any real number c and draw the conclusion that g is a measurable function. G equals f almost everywhere. If f is measurable, then so is g. Next, this thing about restricting the function to a subset of its domain. Consider the set of x values such that f of x is greater than c. Okay, we've taken the domain, we're really cutting it into two pieces, d and E set minus d. So we'll take the x in d, where f of x is greater than c, and union it with the x's in E set minus d, where f of x is greater than c. Union those together gives this set where function takes on values greater than c. We're trying to show measurable here, if and only if measurable there. Well, if f restricted to d is measurable, then this is measurable. If f restricted to E set minus d is measurable, then this is measurable. That's what it means for function to be measurable. Proposition 3.1, part 1, I think it is. Both of these are measurable. The union is measurable. How about if f is measurable on E? Well, if f is measurable on E, what we've got here is the x values, where f of x is greater than c, in E, intersected with D. So here we've taken the set, this measurable set, under the assumption that f is measurable, intersect it with set D, it gives you this. That's an intersection of two measurable sets. Yeah, set D is measurable. That's measurable. This part here is this collection of x values intersected with E set minus D. E set minus D is measurable because E and D are both measurable. This set's measurable, we've intersected, yeah, that's a measurable set as well. So if this set is measurable, then this piece of it is measurable, and so is that piece of it with the intersections properties. And so we draw the conclusion then that both of these are measurable, and so f is measurable on D and f is measurable on E set minus D. Okay. That first property probably is the most useful. We'll be dealing with almost everywhere. Here's an almost everywhere coming up right now. Well, we might be able to do some modifications given what we know from proposition 3.5 part 1. Measurable and equal almost everywhere implies the g function, the other function, is measurable as well. 3.6, let's just go to the statement in the supplements, says, suppose f and g are measurable on E. F and g are extended real valued functions, which are finite almost everywhere on E. Then the linear combination, alpha f plus beta g, is measurable on E for all alpha and beta real numbers. And the product, f times g, is measurable on E. So linear combinations and products of measurable sets are measurable. That's what we get from this. All right, they said finite almost everywhere. Like I was saying, gee, we can, without loss of generality ourselves, statement that f and g are finite on all of E. Well, just change them to maybe 0, where they were not finite, and then you get functions that are equal to the given functions almost everywhere. And almost everywhere is good enough, we saw by proposition 3.5. So there's an illustration already of using the almost everywhere measurability properties. All right, we're going to break part one into two pieces. We're going to do what I would call a scalar multiple piece and then the addition piece, the vector addition piece. Though these ain't vectors. They could be. Somewhere in chapter 6 or 7 or 8, they will be. We'll actually make vector spaces out of functions. But to multiply by scalar alpha, if alpha equals 0, then alpha times f is measurable because that's 0. The 0 function is certainly measurable. It's continuous. If alpha is not 0, then the set of x values for which alpha f of x is greater than c is the same as the set of x values for which f of x is greater than c over alpha. Divide both sides by alpha. Same inequality, same collection of x values. If alpha is negative, then this set of x values, divide both sides by alpha. We get a c over alpha over here, but alpha is negative, so we get the inequality reversed. But anyhow, knowing f is measurable tells you all these sets are measurable, no matter what c is, we're given alpha. Same thing here, no matter what c is, given alpha. These sets equal these sets. Here we've got the function alpha f of x set greater than c, where c is some given real number. And we draw the conclusion, what was it? This is measurable, so the sets on the left-hand side are measurable. These deal with function f, and we hypothesize that f is measurable. These deal with function alpha times f, and we know we get measurability here. So alpha times f is a measurable function. Alpha f is a measurable function for any scalar alpha. How about the addition stuff? Okay, let's consider f of x plus g of x. This is a little weird the way we go at it. I'm going to use rational numbers. Suppose there's an x value for which f of x plus g of x is less than c. You know where we're going with this, right? We want to consider the set of x values in E such that this kind of thing occurs. So that's why we're looking at this, not in connection with the sets just yet, though. If f of x plus g of x is less than c, then move the g of x to the other side. We get f of x is less than c minus g of x. All right, for a given x value, here's a couple of real numbers. There's a little gap between them. This one is less than that one. In that little gap, you can find a rational number, q. There's some rational number, q, that's between f of x and c minus g of x. So, if we take the set of all x values for which f of x plus g of x is less than c, that's the kind of set you want to consider when showing a function, in this case f plus g, a function is measurable. That can be written as the set of all of x values in E such that g of x is less than c minus q. This part holds for the inequality for a rational number. We've written it different. We took the g of x to the left-hand side and the q to the right-hand side, but I'm looking at this little inequality right here. So we move the g and the q around to produce this. And intersect, the other inequality holds. F of x is less than q. That one doesn't need any manipulation. But if both of those hold for some rational number, then we're producing these x values. So what we'll do is union this over all rational numbers for which both of these hold will produce the collection of x values for which f of x plus g of x is less than c. Why did you appeal to rational numbers? Why not use irrational numbers? Because there's an irrational number in between as well. So we get a countable union over here. And then we can use sigma algebra properties. So it was to get the thing countable. We're working with a hypothesis that f and g are both measurable. If f is measurable, this is a measurable set. Function value is less than some real number. It's a real number q in this case. Measurable if f is measurable. If g is measurable, here we've got x values such that g of x is less than this real number. Measurable because g is a measurable function. These kinds of sets are measurable. These kind of sets are measurable. So all this union and intersection stuff produces that this is also a measurable set using the sigma algebra properties of calligraphy and the Lebesgue measurable sets. If this is measurable, then f plus g is a measurable function. Okay, so that takes care of the scalar multiplication. Up here, the alpha f part. Down here, the vector addition, if you will. And combining those two, we get the linear combination stuff. So we dealt with those separately, but linear combinations we now have of measurable functions are measurable. On to the product of measurable functions. Okay, this is fairly straightforward. Deals with some algebraic manipulations. Notice that f of x times g of x can be written as 1/2 f of x plus g of x, quantity squared, minus f of x squared minus g of x squared. That'll work for any x value on which those functions are defined. Yeah, square this out, FOIL it. The first is f of x squared. That'll cancel with this. The last gives g of x squared, cancels here, and you're left with the cross terms. You get 2 f of x g of x. Well, that's why there's a 1/2 out front. So indeed, that's an algebraic identity. So take c to be a real number. First, suppose it's not negative. C is greater than or equal to 0. If we look at the x values for which f of x squared is greater than c, that comes in 2 parts. That requires, dealing with the inequality and the square roots, that requires either f of x is greater than the square root of c, or f of x is less than negative square root of c. Solving this inequality the usual algebra way will produce these 2 inequalities. So x values that satisfy this condition satisfy either this condition or that condition. By the way, we've assumed that f was measurable in this, so this is a measurable set. So this is a measurable set. These are those 4 types of things we were discussing in Proposition 3.1 that led us to our definition of measurable function. So these 2 sets are measurable sets. Their union's measurable, so we get that this is a measurable set. Only half the story because that assumes c was non-negative. If c is less than 0, then the x values for which f of x squared is greater than c, well, if c is negative, or squaring real numbers, that'll be all possible x values. So that'll be set E, which is measurable by hypothesis. Anyhow, in both cases, since f is measurable, we see that these types of sets, for C a real number, are measurable sets. And there you go. That means that the function concerned, the f of x squared function, is a measurable function. What we've just shown is if a function is measurable, then its square is measurable. Well, then a similar argument would show that, that g squared is measurable. Same argument. If f and g are measurable, then f plus g is measurable. That's part 1. And we know squares of measurable functions are measurable. So f plus g squared is a measurable function. Awesome. So we've got this is measurable, this is measurable, and this is measurable. We've taken a linear combination of these 3 functions, f plus g squared, f squared, and g squared. Some linear combination to produce f times g. You know, linear combinations of measurable functions are measurable, and we have fg written as a linear combination of functions we have now shown to be measurable. So fg is measurable, and products of measurable functions are measurable. Okay, compositions behave in a slightly more awkward way. The textbook gives an unusual example based on the Cantor-Lebesgue function from the tail end of chapter 2. There are 2 real valued measurable functions defined on R whose composition is not measurable. So we're not going to say compositions of measurable functions are measurable. Here's a counterexample to that, or the location of one in the book. Page 57 of the textbook, they use the Cantor-Lebesgue function to show that this need not happen. I can compose 2 measurable functions to get a non-measurable function. We need more hypotheses than just measurable when we look at compositions, and that's what the next result gives. Suppose G is a measurable real-valued function. They say real-valued versus extended real-value. This is context that they're using that in. G is a measurable real-valued function defined on E, and F is a continuous real-valued function defined on all of R. Okay, so they're putting some constraints on the F function, continuity and defined on all of R. Then the conclusion is the composition F composed with G is measurable on E. The G function goes inside the F function, so whatever comes flying out of the G function, F's got to be able to deal with. So with no other hypotheses, that'll do it. If F is defined on all real numbers, then the composition is defined. So I don't care what comes out of the G function, the F function has that in its domain. But this seems like quite a constraint here. They're requiring continuity. So let's look at the proof. Okay. Take an open set. Then F composed with G inverse of an open set, that is G inverse of F inverse of the open set. Doing the function composition, inverse image stuff with function composition. We know that since F is continuous, F inverse of O is open. Inverse images of open sets are open with respect to the domain of a function. That's the senior level analysis 1 result we mentioned earlier. Inverse images of open sets are open with respect to the domain of the function. All right, so F inverse of O is an open set. G is measurable. Proposition 3.2 tells you that under a measurable function, inverse images of open sets are measurable. So G inverse of this open set, F inverse of O, is measurable. And we just took an arbitrary open set and showed that its inverse image under this composition is measurable. Proposition 3.2 said inverse images of open sets are measurable if and only if, dealing with measurable functions. So we can apply 3.2 again to draw the conclusion that if F composed with G inverse image of O is measurable, then that function, F composed with G, is a measurable function, proposition 3.2. So this one is well coming as an easy result following from 3.2. Back to the notes. Okay, one final thing to prove. Let's see, proposition 3.7 dealt with compositions, certain constraints. Proposition 3.7 implies for F a measurable function, the absolute value of F is a measurable function. So we've composed the absolute value function with the function F. Is the absolute value function defined on all the reals? And is it continuous? Yeah. Well, then there you go. Then the absolute value of F is a continuous function. Taking the composition, the outer function being the absolute value function, the inner function being some measurable function F. Also, absolute value of F to the P power, where P is greater than 0. That'll be a measurable function as well. We'll deal in section 4.4 when we're trying to integrate functions that can be maybe both positive and negative. We'll integrate those functions, and in so doing, we'll deal with the absolute value of F. So at that time, knowing this gives us a measurable function will be a useful thing. In chapters 7 and 8, we'll deal with something called LP spaces. LP spaces are heavily dependent on a quantity like this, the absolute value of F to the P power. Actually, we'll take P greater than or equal to 1 in those settings, and these will be used to set up a norm on a certain linear space. These LP spaces, the L is for linear. So these are linear spaces. They're closed under linear combinations. And what it means to be in these spaces is related to integrals of this sort for a given p-value greater than 1. So details to follow on that. But this result here that we know that the absolute value of f to the p power is a measurable function whenever f will be useful in computing those norms in that linear space. So last little result, and we'll get a bit of mileage out of this. We're really foreshadowing how we'll use these measurable functions down the road. It says, for a finite family f sub k, k equals 1 to n, finite collection of measurable functions with a common domain E, the functions, the two functions defined as the maximum, pointwise maximum, of f1 through f sub n, and the minimum of f1 through f sub n, defined pointwise. These are all measurable functions. So what we'll do at a particular x value is plug that x value into each of these functions and pick the largest resulting number for the value of the max function, or the smallest output for the min function. There will be a largest and a smallest because we just got a finite collection of numbers here. Let's look at the proof of that. All right. For any real number c, when we look at the maximum over that finite collection of functions, when the maximum of the functions is greater than c, we can write that as a union from 1 to n of x values for which the kth, f sub k of x is greater than c. Think of it like this. If we've got x values where the function is greater than c, then the maximum will certainly be greater than c. So if any of these is greater than c, then the maximum one is certainly greater than c. Maybe interpret it like that. Minimum, when we look at the minimum of this collection of functions, minimum is greater than c. We can write that similarly as an intersection. And these are just finite intersections of x values for which f sub k of x is greater than c. The benefit of writing it like this, of course, is we've hypothesized these functions are measurable. And we're trying to show this function, remember that's a single function, and this function. Trying to show those two functions are measurable. So we need to relate these function values greater than c for these two kinds of functions to function values greater than c for the collection of k functions that we're given. This does it. Each of these will be measurable on the right-hand side, so their finite union and intersection will be measurable. Each of the right-hand sides are measurable. We're in a sigma algebra, so these unions and intersections are measurable, and so these sets are measurable. C was an arbitrary real number, so this function is measurable, and that function is measurable. So the max and the mins of these collections of functions are measurable. Max and min, that doesn't sound very analysis-ish. I wonder if this would work for soups and nths. Back to the notes for some final observations. Proposition 3.8 can be extended to soups and nths. Okay, that might lead to some extended real values for sure. Soups and nths can be extended real numbers. But the result also holds for soups and nths of countable collections of measurable sets, I guess it is. So if we have a countable collection of measurable sets, then we could say the soup of that collection of sets dealt with pointwise, and nth dealt with pointwise. Those two functions are also measurable functions. It's an exercise, 3.21. Of more immediate use is the following. If we take a measurable function f of x and we define a new function to be the maximum of f of x and negative f of x, what you're getting out really pointwise is simply the absolute value function. The absolute value function then is a measurable function. We made this observation at the top of this page, I think, but there's another argument for it following from that other result using the max mins. And these two functions, defined as f plus and f minus. F plus is the maximum of f of x and 0. So what this function is function f when function f is non-negative, and 0 when function f is negative. So you've basically chopped off the bottom of this f of x function along the x-axis. Anything that dropped below the x-axis, you chopped it off and gave the function the value 0. The negative part of a function, okay, this looks a little bit weird. It's the same idea. You might think lawnmower style. To get the negative part of the function, I'll just run the lawnmower along the x-axis and chop all the stuff above off. That is rounded down to 0. And that should be the negative part. Well, sort of. You've done that, but then you flipped it over and introduced a negative sign here. So what you're keeping is the values where the function was negative, but it's spitting out positive values. So this is weird. The positive part of a function is positive. The negative part of a function is also positive. The geometry's there. You've kept the values where the function was negative, but you've changed them to make them positive. If you'll add the positive and the negative part together, you'll get the absolute value. Fret not over the details of that too much right now. We'll draw pictures later. And we'll use this quite a bit in section 4.4 when we're looking at the general Lebesgue integral. We'll initially integrate non-negative functions. And once we have non-negative functions integrated, we'll break them into positive and negative parts. Notice the positive part's positive, and for some psychotic reason, so is the negative part. It's that reason. We'll first integrate positive functions. Then when we reach the functions that might be positive or negative, we'll break them into these two parts, both of which are positive. And we'll know how to integrate the positive part, and we'll know how to integrate the negative part. So there's reasons for these odd definitions, but this will appear later, and the measurability of the positive and negative part follows from that proposition 3.8 that we just saw. So there's an intro to measurable functions. Our ultimate goal is to define the Lebesgue integral for every measurable function. It won't quite work. As long as we avoid some sort of infinity minus infinity computations that might pop up. It might pop up when we break these functions into positive and negative parts and get infinity for both of the integrals of those over appropriate sets. As long as we avoid the infinity minus infinity, we will integrate all measurable functions. That's what the section on the general Lebesgue integral is all about. What we'll do next is go through and approximate measurable functions with certain kinds of functions. And everything we do, we got an eye on dealing with ripping off Riemann and doing something like rectangles and Riemann sums, but using measurable functions. And the rectangles will still have a base and a height, and the height will still be based on function values, but the base will be more complicated. It won't be a little interval anymore. It'll be a measurable set. If we deal with continuous functions, maybe it will be an interval. Remember, the measure of an interval is its length. The reason we were so insistent on that is when we start making Riemann rectangles versus Lebesgue rectangles, in the common ground, they do the same thing. So Lebesgue does the same thing Riemann does when Riemann works, but Lebesgue is going to work for a whole bunch of other functions, and it'll come with a more robust theory. That's the reason we're doing this Lebesgue integration stuff. All right, I will see you next in section 3.2, and we'll look at approximating functions in a way motivated by an idea of little rectangles. I'll see you in section 3.2.